Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
So, I want you to imagine for just a second that you've walked into a dealership, right? And you decide to buy a brand new, absolute top-of-the-line luxury car.
Okay, like a real high-end custom-built situation.
Exactly. I mean, we are talking state-of-the-art engineering here. You spend a ridiculous amount of money on it, literally millions of dollars.
Right.
You custom order all the features. The leather is completely perfect. The electronics are, smarter than most desktop computers, and it just drives like an absolute dream.
Sounds like a great investment, honestly.
It does. And here's the thing. There is one tiny, completely absurd catch to this transaction. The manufacturer has completely welded the gas tank shut.
Oh, wow. So there's no fuel cap at all.
None. Zero. No access port whatsoever. You basically drive it off the lot knowing that there is absolutely no physical way to ever put more fuel into that machine.
Which is just, that's financial insanity.
Right. And you just accept it. You drive this incredible machine for years.
Yeah.
Maybe you get a solid decade out of it, pulling massive value from the investment.
Because it functions perfectly otherwise, right?
Exactly, yeah. The engine is flawless, the transmission is buttery smooth, the computers are sharp. But eventually, inevitably, the laws of physics catch up with you, and that needle finally hits empty.
And because you can't refuel it?
Because you can't put gas in it, your only option is to pull over onto the shoulder of the highway, turn off the engine, walk away, and just leave a multi-million-dollar masterpiece to sit in the dirt and rot.
And then go buy a new one.
And then go back to the dealership and buy a brand new one.
Yeah. If any industry on Earth actually operated that way, we'd call it a scam. You would never accept that level of built-in obsolescence in your daily life. It just defies basic economic logic.
But the wild thing is, historically, this exact throwaway culture, it's been precisely how humanity has managed our most expensive, most complex machines.
Yeah, it really has.
For over half a century, this is exactly how we have treated the multi-million-dollar satellites orbiting our planet. I mean, once the fuel on board is gone, the satellite is just dead.
We literally abandoned the car on the side of the cosmic highway.
Exactly. We just walk away.
And it's driven entirely by the unforgiving physics of space travel.
Yeah.
And just the sheer cost of getting mass out of Earth's gravity well.
Right, because it takes so much effort just to get it up there.
Yeah, you spend all your energy just surviving the violent vibration of a rocket launch. Historically, you send a machine into the void, and the void is a one-way trip.
There's no AAA to call.
No, you can't send a mechanic up there. Once it's up there, it is completely on its own. It's a sealed system just ticking down to its eventual death.
Well, the era of abandoning that car on the side of the highway is officially ending, like right now.
It's a massive shift.
It is. The reality we are stepping into this month is staggering. We are basically witnessing the birth of a brand new orbital economy.
Yeah, orbital tow trucks.
Exactly. We are talking about robotic salvage operators, tow trucks, and space mechanics actively jumping into the void to fix things. It's a fundamental shift in how we manage the space above our heads.
And July 2026 is really proving to be the absolute turning point for this transition. We're currently watching two incredibly groundbreaking missions happening simultaneously right now.
Which is just so cool to watch unfold.
It really is. We have private companies deploying these highly specialized spacecraft, essentially acting as robotic service stations, and deploying orbital jetpacks to go out, track down aging technology, and physically breathe new life into them.
Yeah, and saving a fortune in the process.
Oh, we're talking about saving billions of dollars in replacement costs and entirely rewriting the rule book on how long the spacecraft is supposed to live.
Okay, so let's unpack this and look at the mechanics of how they're actually pulling this off. Because honestly, the logistics feel like something ripped straight out of a sci-fi novel.
They really do.
Let's start with the big one, the AAA of space. On Tuesday, July 21st, 2026, we saw a massive launch out of Cape Canaveral in Florida. A SpaceX Falcon 9 rocket blasted off, but it wasn't carrying your typical communications satellite, and it wasn't, a telescope looking out into the deep universe. It was carrying a piece of hardware called the MRV.
The Mission Robotic Vehicle, designed and built by Northrop Grumman. And the MRV is a completely different beast compared to the sort of passive technology we usually hurl into orbit.
Right. Usually things just sit there.
Yeah. A traditional satellite is designed to look down at the Earth or look out at the stars and largely just stay out of the way of everything else. But the MRV is designed to actively hunt down other human-made machines.
It's like a predator.
An active predator, yes, but for maintenance.
To give you a sense of scale for this thing, I want you to picture a heavy-duty commercial minivan. That's essentially the main central body, the chassis of the MRV.
Basically a flying minivan.
Yeah, but bolted onto this minivan are two massive, highly articulated robotic arms, and they are 10 feet long, so about 3 meters each. So basically have a minivan with giant mechanical arms hurtling through the freezing vacuum of space.
And those arms are a staggering piece of engineering on their own, really.
Right.
Because think about what happens to machinery in space. We take lubrication for granted on Earth.
Right, you just add some oil.
Exactly. If you have a robotic joint, you grease it. But in a vacuum, liquid lubricants instantly boil off or they freeze solid.
Oh, wow. I didn't even think about that.
Yeah. And furthermore, a satellite moving in and out of Earth's shadow experiences temperature swings of hundreds of degrees in a matter of minutes.
That sounds brutal on the metal.
It is. The side of the robotic arm facing the sun is baking and physically expanding, while the side in the shadow is freezing and contracting. So getting a 10-foot arm to maintain millimeter precision while fighting extreme thermal distortion and having no standard lubrication, it's a massive metallurgical achievement.
That is just wild. And the thing is, it didn't just go up as an empty tow truck. It brought its own payload with it. The MRV launched alongside 3 separate modules. You can think of them as orbital jetpacks or what Northrop calls mission extension pods.
The MEPs.
Yeah. And each of these jetpacks is roughly the size of a standard washing machine. But they aren't using traditional chemical rocket fuel. You aren't going to see a massive plume of fire shooting out of the back of them.
No, here.
These are electric-propelled modules equipped with xenon gas thrusters.
And the choice of xenon is incredibly specific for this kind of mission. A chemical rocket, like the Falcon 9 that brought them all up there in the first place, relies on a violent chemical reaction.
The big explosion.
Exactly. You mix liquid oxygen and kerosene, ignite it, and you get an explosion that pushes you upward. It's incredibly powerful, but it burns through thousands of pounds of fuel in minutes.
Right, which you can't really do if you're a washing machine up in space.
Exactly. So these jetpacks use Hall effect thrusters. They take xenon, which is a very heavy, inert, noble gas, and they trap electrons in a magnetic field.
Okay.
And they use those electrons to ionize the xenon gas, essentially giving the gas a positive electrical charge.
And then they use an electric field to shoot that ionized gas out the back of the thruster, right?
Exactly. It throws the xenon atoms backward at phenomenal speeds. We're talking sometimes upwards of 30,000 to 100,000 miles per hour.
Wow.
Because xenon atoms are so heavy compared to other gases, shooting them out the back generates a very steady, highly efficient thrust. You aren't burning fuel in the traditional sense.
You are electrically accelerating atomic bowling balls out the back of the spacecraft.
That is a perfect way to describe it. Atomic bowling balls.
So the choreography of how this all unfolds in orbit is what completely broke my brain when I was looking into this. Because the MRV and the 3 washing machine jetpacks, they all go up together inside the fairing of the Falcon 9. But once they hit the vacuum of space, they don't stay attached.
No, they disperse. Following liftoff and insertion into the initial orbit, those 3 jetpacks actually physically detach from the main MRV minivan.
They just pop off.
Yeah, and because they have their own independent xenon thrusters and navigation systems, they don't need the MRV to carry them the rest of the way. They basically fly themselves out to their designated orbital parking spots.
And then what?
They position themselves and then just power down their main drives and wait.
They just hang out in the void, completely alone.
Exactly. They wait for the MRV to do the heavy lifting. The MRV, the minivan with 10-foot arms, is going to fly around, track down the first jetpack, use its robotic arms to physically grapple it, and then carry that jetpack over to a completely different, older, out-of-gas communication satellite.
Like a dedicated delivery driver.
Right. The MRV will then physically plug the new jetpack into the dying satellite, effectively giving it a brand new engine and gas tank. The old satellite can now steer again.
And then the MRV is done.
With that one, yes. Once it's securely attached, the MRV lets go of the jetpack, zips off into the void to find the second jetpack, and repeats the entire surgical process for another dying satellite.
It's honestly like a handyman walking around your neighborhood carrying spare batteries, plugging them into the dying smoke detectors in your house.
Yeah.
But the house is thousands of miles wide, pitch black, and floating in a vacuum.
It's a very large, very dangerous house.
But this is where I have to pause and look at the logic of the operation. Because if these jetpacks have their own xenon thrusters, right, and they have the onboard computer brains to peel away from the rocket and fly themselves to the right general orbit.
Yes, they do.
Then why do we even need the giant minivan-sized robot arm to plug them in? If the jetpack can fly, why can't it just fly right up to the dying satellite and dock itself?
That points to the central mechanical nightmare of this entire industry. The limitation has nothing to do with the cutting-edge technology of the new jetpacks.
Oh, really?
Yeah, the limitation is the archaic design of the old satellites they're trying to save. The communication satellites currently running out of gas were built 10, 15, or even 20 years ago.
Different era of tech.
Completely different. Back then, the concept of orbital docking was strictly reserved for massive government projects, like the International Space Station or the Space Shuttle. A standard commercial television or internet satellite was built to be launched once and never touched again.
So they didn't build in a way to grab them.
Exactly.
Yeah.
They do not have docking ports. There's no standard USB slot to just click a new engine into.
So they are essentially trying to dock with a completely smooth, uncooperative metal box.
A metal box covered in incredibly fragile, highly expensive solar panels and delicate communication antennas. There are no designated attachment points, no laser-guided docking rings.
So you can't just bump into it.
No, you absolutely cannot just bump a washing machine-sized jetpack into a satellite and hope it miraculously sticks. If the jetpack tries to dock itself, it risks smashing into a solar array and instantly creating millions of dollars of space debris.
Which means you need the tactile manual intervention of the MRV.
Right. You need a highly sophisticated intermediary. You need those 10-foot robotic arms to carefully approach the dying satellite, reach out, and manually grapple the only solid piece of structure available.
Which is what? What can they even grab onto?
Usually it's the original dead rocket nozzle of the old satellite's main engine.
Wow, okay.
The MRV has to grab that dead nozzle, stabilize the entire massive structure, and forcibly marry the new jetpack to the old satellite. It requires physical leverage, precise alignment, and an incredibly delicate touch.
I want to talk about the physics of that for a second, because think about the last time you tried to delicately parallel park your car on a tight street.
It's stressful enough on Earth.
Right. Now imagine trying to do that, but the car you are trying to park next to is moving at thousands of miles an hour and neither of you have brakes.
Yes.
And on top of that, you were dealing with Newton's third law in a vacuum. Every action has an equal and opposite reaction. So if the MRV reaches out with a mechanical arm and pushes the new jetpack into the old satellite to lock it in place, doesn't the act of pushing just propel the MRV backward?
It absolutely does. And this is why orbital robotics is so astonishingly difficult. If you imagine standing on a frictionless sheet of ice while wearing ice skates, right?
Okay, yeah.
And someone hands you a bowling ball, and you try to shove that bowling ball into a very specific slot on the wall.
You're going to slide backward?
The moment you push the ball forward, your skates slide backward. The MRV has to constantly counteract its own mechanical forces. As the 10-foot arm pushes the jetpack forward into the dead engine nozzle of the target satellite, the MRV's own tiny attitude control thrusters have to fire in the exact opposite direction.
Just to cancel out the push.
Yes, with a precise amount of counterforce to keep the minivan stationary. If they miscalculate the thrust, they either bounce off the target or they smash straight through it. It is an intricate ballet of force and counterforce.
And the old satellite is essentially just a 5,000-pound brick at this point.
Basically, yeah.
It cannot stabilize itself. It can't adjust its attitude to help the MRV catch it. It is a completely passive target. So the MRV has to do 100% of the heavy lifting to make the connection safe.
Which is exactly why having a specialized, reusable robotic vehicle is the only way to perform this operation safely. And this is but the mechanical nightmare of catching that frictionless bowling ball is really only half the battle. Okay. The other half is the commute.
Right, because the location where this high-stakes intervention is taking place completely upends how we normally think about space travel timelines.
Oh, absolutely.
We are not talking about something flying just above the atmosphere where the space station lives. The MRV and these jetpacks are heading to geosynchronous orbit.
Geosynchronous orbit, or GEO. This is the absolute prime real estate of the global space economy. We are talking about a very specific, highly contested ring around the Earth's equator, situated a staggering 22,300 miles away.
Which is just a massive distance.
It's huge. In kilometers, it's roughly 36,000 kilometers straight up. Just to give you some perspective, the International Space Station orbits at about 250 miles above us.
So 250 miles versus 22,000 miles.
Right. The MRV is going nearly 100 times further out into the deep void.
And if you're wondering why anyone would bother parking a satellite 22,000 miles away when we have perfectly good orbits right next door, it all comes down to the physics of angular velocity. Why is that specific altitude so unbelievably valuable?
It is entirely about matching the speed of the Earth's rotation. The closer a satellite is to the Earth, the faster it has to travel to avoid falling back into the atmosphere due to gravity.
Because gravity is pulling harder when you're closer.
Exactly. So the space station orbits the Earth completely once every 90 minutes. It is constantly rising and setting. But as you move further away from the Earth, gravity's pull weakens, meaning a satellite doesn't have to travel as fast to stay in orbit.
So its orbital period, the time it takes to go around the Earth, once just gets longer and longer the higher you go.
Precisely. And in 1928, an engineer named Herman Potočnik calculated, and later Arthur C. Clarke popularized, a very specific mathematical sweet spot.
Okay, what's the sweet spot?
If you push a satellite out to exactly 22,300 miles above the equator, the time it takes for that satellite to complete one orbit around the Earth is exactly 23 hours, 56 minutes, and 4 seconds.
Which perfectly matches the time it takes for the Earth to complete one rotation on its axis.
Exactly. So to an observer standing on the ground, a satellite in geosynchronous orbit appears completely motionless in the sky.
That's wild. It just hangs there.
It stays locked over the exact same patch of the planet, 24 hours a day, 7 days a week.
And this is the entire foundation of modern global communication. If you are a satellite television provider or, a company running secure financial data across an ocean, you need your customers to be able to bolt a dish to their roof, point it at one specific unmoving spot in the sky, and never have to touch it again.
Because if it moved, it would be a nightmare.
Right. If the satellite was in a lower orbit, it would zoom across the sky like a shooting star. You would need a dish with complex motors tracking it constantly, and you'd lose the signal every single time the satellite dipped below the horizon.
But in GEO, you get continuous, uninterrupted coverage over an entire continent. That is why hundreds of our most critical, most expensive communication satellites are clustered out in that one specific ring.
It's basically a multi-billion-dollar orbital parking lot.
That's exactly what it is.
Yeah. But getting to that parking lot takes a shocking amount of time. I mean, this launch we are talking about happened in July 2026. The Falcon 9 dropped them off in space, but the first actual satellite rescue, the first time those robotic arms grab a jetpack and plug it into a dying satellite, won't happen until mid-2027.
Right.
It is going to take a full year for the MRV and the jetpacks just to get into position.
A full year of immense patience. And this brings us back to those xenon gas thrusters we mentioned earlier. The physics of electric propulsion dictate a completely different timeline that we are used to seeing in space exploration.
Because with a chemical rocket, a trip to the moon, which is 10 times further away than GEO, only takes 3 days. So why does it take a year to go a fraction of the distance?
It comes down to a concept called the tyranny of the rocket equation and the trade-off between thrust and specific impulse. Chemical rockets give you a massive, instantaneous burst of acceleration.
They kick you out fast.
They can kick you out to the moon in a matter of days. But to get that power, they have to burn an astronomical amount of heavy liquid fuel. If you tried to pack enough chemical fuel into the MRV to constantly maneuver and rescue multiple satellites, the vehicle would be the size of a skyscraper.
And you just couldn't launch it.
Right. No rocket on Earth could lift it off the launch pad.
So you have to sacrifice the immediate burst of speed for long-term efficiency.
Exactly. Electric thrusters ionizing that xenon gas provide an incredibly high specific impulse, meaning they're vastly more efficient with their fuel. But the physical thrust they produce at any given moment is microscopic.
I've heard it compared to the weight of a piece of paper resting on the palm of your hand. That is the physical amount of push the thruster gives the spacecraft.
It is an incredibly gentle, almost imperceptible nudge. If you fired a Hall effect thruster on Earth, it wouldn't even be able to push itself across a slick floor.
Really? That weak?
That weak. But in the vacuum of space, where there is zero air resistance and zero friction, that tiny continuous push of a piece of paper builds up over time. Because the xenon system is so highly efficient, The MRV can fire that thruster continuously for months on end.
So it's not pointing straight up and firing. It's moving in circles around the Earth, constantly firing that tiny thruster, slowly spiraling outward inch by inch, mile by mile, for 365 days.
It takes a year, yes, but it allows the spacecraft to remain incredibly light and compact. It frees up mass so the vehicle can actually carry the heavy, complex, robotic arms and the multiple jetpacks.
Which brings up a massive economic question for me.
Okay.
If you are an operator sitting in a control room on Earth and you are watching your $400 million satellite slowly run out of maneuvering fuel, and you know it takes an entire year just for the tow truck to arrive, why wait?
Well, because...
does it make more sense to just cut your losses, call the manufacturer, build a brand new satellite on Earth, and launch it on a fast chemical rocket?
No.
Why undergo this year-long wait for a robotic mechanic?
Because the mathematics of waiting a year represent the bargain of the century for these corporations. We have to look at the difference between capital expenditure, CapEx, and operating expenditure, or OpEx.
Okay, walk me through the numbers.
Building a brand new communication satellite designed to survive in deep space for 15 years is a staggering CapEx investment. You are looking at $300 to $400 million just to manufacture the bus, the solar panels, and the transponders.
That's before it even leaves the ground.
Exactly. Then you have to buy a dedicated heavy-lift rocket to get it out to GEO, which is another $50 to $100 million. And you have to pay astronomical insurance premiums just in case the rocket explodes on the pad.
And meanwhile, the old satellite up there is technically still perfectly fine.
Yes.
The antennas still transmit data perfectly. The solar panels are still generating electricity. The computers are still crunching numbers. It's a completely functional multi-million-dollar asset that just can't keep its antennas pointed at Earth because it's out of the tiny puffs of gas needed to keep it balanced.
That is the tragedy of the throwaway culture. You are discarding $500 million of perfectly good technology for the want of a few kilograms of propellant. Now look at the alternative the MRV provides.
Right, the rescue mission.
If you are SES based in Luxembourg or Optus based in Australia, two of the major telecommunication operators who have contracted this specific MRV mission, you're looking at a dying asset that still has enormous revenue generating potential.
Because they already paid off the mortgage on the old satellite. Every year it stays active as pure profit at that point.
Exactly. And by paying a fraction of the cost of a new satellite, say $30 to $50 million for this robotic jetpack delivery, you extend the life of your asset by another 5 or 6 years.
You turn a devastating write-off into a prolonged revenue stream.
You wait the year because the return on investment is mathematically undeniable. In space, you aren't really paying for the hardware. You are paying to preserve the location and the momentum that the asset already possesses, which is the most expensive commodity in the universe.
Yeah. I find the business logic of that fascinating. It's the ultimate exercise in deferred gratification. You wait a year in the dark, but you save yourself $250 million in capital outlay.
That's just smart business.
And it completely shifts the paradigm from disposable assets to a long-term managed fleet.
It proves that maintaining assets in space is now a long-term logistical game with an entirely new supply chain.
But, the reality of space is that you don't always have a year to wait.
No, absolutely not.
While the MRV is playing this slow, patient, year-long game of orbital chess out at 22,000 miles, there is a completely different salvage mission happening right now that is the exact opposite in every conceivable way.
It's a sprint instead of a marathon.
Exactly. While Northrop Grumman takes its time spiraling out to the deep void, another spacecraft is rushing frantically to stop a multi-million-dollar asset from literally falling out of the sky this fall.
Right.
We are talking about a high-stakes emergency happening much closer to home.
The contrast between the two operations really highlights the sheer breadth of this new economy. Here, we're moving from a patient commercial upgrade in the deep void to an urgent scientific rescue in low Earth orbit.
A rescue mission.
And the asset in distress here isn't a corporate communication relay. It is NASA's Swift Observatory.
The Swift telescope is an incredible piece of scientific machinery with a phenomenal legacy. It was launched way back in 2004. So it has been operating in the harsh environment of space for over 2 decades.
It's had a long life.
It's a nearly $400 million gamma ray observatory. And its sole purpose, its entire reason for existing, is to study the absolute most violent, biggest explosions in the known universe.
Gamma ray bursts, or GRBs, are truly phenomenal astronomical events. They are the most luminous, highly energetic explosions in the universe since the Big Bang itself.
Just massive amounts of energy.
When we detect a GRB, we are usually witnessing the violent, catastrophic death of a massive star collapsing inward to form a black hole, or the cataclysmic collision of two neutron stars. The energy released in a few seconds is more than our sun will emit over its entire 10 billion year lifetime.
That is just, that's almost incomprehensible. But the challenge for astronomers is that these bursts are incredibly fleeting, right? The universe doesn't give you a warning.
No, not at all.
A patch of dark sky suddenly erupts with gamma radiation, and it might last a few minutes or it might be over in a few milliseconds.
Which is exactly why the telescope is named Swift. It was engineered with highly advanced gyroscopes and reaction wheels. The moment its wide-field monitors detect a flash of gamma rays anywhere in the deep universe, the entire spacecraft autonomously and violently swivels itself to point its high-resolution X-ray and optical telescopes directly at the fading afterglow.
It has to catch it before the light vanishes. It is essentially a cosmic first responder, and it has been fundamentally vital for high-energy astrophysics for 20 years. But unlike the communication satellites sitting comfortably out in the frictionless void of geosynchronous orbit, Swift operates in low Earth orbit, or LEO.
Which is a very different environment.
It sits about 373 miles, or 600 kilometers, above the surface of the Earth. And that specific altitude comes with a very dangerous, constantly shifting hazard.
Atmospheric drag. We commonly think of space as a total, perfect vacuum the moment you cross the Kármán line at 100 kilometers. But the reality is much messier. Even at 600 kilometers up, you are still technically skimming through the exosphere.
Which is what, exactly?
It's the absolute outermost wispy edges of Earth's atmosphere.
So there are still trace amounts of oxygen and nitrogen molecules floating around up there.
Exactly. And when a spacecraft moving at 17,000 miles per hour collides with even these incredibly sparse microscopic molecules, it creates friction. Over time, that friction saps the kinetic energy of the satellite. It loses momentum.
And speed equals altitude, right?
Yeah. The brutal law of orbital mechanics is that speed equals altitude. When you lose speed, gravity starts winning the tug of war. You slowly, inexorably sink back toward the Earth.
But wait, Swift has been up there dealing with this trace atmosphere for 20 years, and it's been totally fine. So why is it suddenly a dire crisis right now? Why is it falling so fast in 2026 that NASA's terrified it might burn up in the atmosphere this fall?
Because the density of the atmosphere at that altitude is not constant. It is entirely dictated by the mood of the sun.
The mood of the sun.
Our sun operates on a rough 11-year cycle of magnetic activity, shifting from a quiet solar minimum to a violently active solar maximum. We are currently in a period of intense solar maximum. The sun is highly active, throwing off massive coronal mass ejections, solar flares, and bathing the Earth in intense extreme ultraviolet and X-ray radiation.
And when all that extra solar energy hits the top of Earth's atmosphere, it heats it up.
And just like a hot air balloon, when you heat a gas, it expands. The Earth's atmosphere physically puffs outward, expanding further into space.
Okay, so the atmosphere is literally getting taller.
Altitudes that used to be a near-perfect vacuum during solar minimum suddenly become densely packed with air molecules. The thermosphere swells up and engulfs satellites that thought they were flying in clear space.
So Swift is suddenly hitting a literal wall of air it wasn't designed for. The drag coefficient on its specific aerodynamic profile has just skyrocketed.
NASA flight controllers realized that because of this aggressive, expanding solar activity, Swift's orbit was decaying dramatically faster than their models predicted. It is sinking.
And if they don't do anything?
Without an immediate physical intervention, this $400 million telescope will inevitably hit the thicker lower parts of the atmosphere and be incinerated in a fiery reentry.
Enter the rescue mission. NASA doesn't have a year to wait for an electric thruster to slowly spiral out to it. On July 3rd, 2026, a company called Katalyst Space Technologies launched their Link satellite helper on a desperate intercept course.
A true rapid response mission.
And the way they launched this rescue module is just as fascinating as the mission itself. The MRV went up on a standard Falcon 9 rocket, taking off vertically from a concrete launch pad with a massive explosion. The Link mission used a completely different, highly specialized approach provided by Northrop Grumman, a Pegasus rocket.
The Pegasus launch system is a brilliant piece of aerospace engineering. It's specifically designed for small payloads that need to get to orbit fast. Instead of launching from a stationary pad on the ground, the Pegasus rocket is carried up into the air horizontally, strapped to the belly of a heavily modified commercial airliner.
A jet plane.
A customized Lockheed L-1011 known as the Stargazer.
So they just fly a massive passenger jet up to about 40,000 feet, open the bomb bay doors, drop a 50,000-pound rocket out from underneath it, and the rocket just ignites midair while falling.
That is the exact mechanism. It's called an air launch system. And the physics behind why you would do this are incredibly sound. Rockets use the vast, overwhelming majority of their fuel in the first 2 minutes of flight, just pushing through the absolute thickest, most dense part of the lower atmosphere and fighting stationary inertia to get off the pad.
Right. The air is really thick down by the ground.
This period of maximum aerodynamic stress is called max Q.
So it takes an immense amount of energy just to punch through the thick air at sea level.
By carrying the rocket inside an airplane above 40,000 feet, you essentially skip the hardest part of the atmosphere. The airplane does the grueling work of climbing through the thick air. When the Pegasus drops, it is already above 75% of the Earth's atmosphere, and it already has a starting lateral velocity of about 500 miles per hour from the jet.
It's getting a massive head start.
The rocket requires vastly less fuel to reach orbital velocity, meaning it can be much smaller, much cheaper, and launched from almost anywhere in the world on a moment's notice. For a small, urgent payload like Katalyst's Link module racing to catch a falling telescope, it is the ultimate rapid deployment system.
So they drop the Pegasus, the rocket screams into low Earth orbit, and the Link module deploys. But the drama immediately begins. Because, space is inherently hostile. Before Link can even begin to think about rushing over to save the Swift telescope, Link itself runs into severe trouble in the void.
Which is terrifying when time is running out.
Flight controllers back on Earth start seeing initial communication glitches and physical pointing problems with the hardware in orbit.
This is a classic, brutal reality of spaceflight. You can test hardware in a thermal vacuum chamber on Earth thousands of times, but the actual space environment will always throw unpredictable curveballs.
It's just a totally different beast up there.
The extreme temperature fluctuations, the micro vibrations of deployment, and the constant bombardment of cosmic rays, causing single event upsets in the computer processors, commercial off-the-shelf hardware, often struggles in the first few weeks of operation.
But the engineers at Katalyst managed to fix it. And the way they fixed it is a testament to modern engineering. They fixed physical pointing problems entirely remotely, just beaming up complex software patches to correct the hardware anomalies.
They had to rewrite the attitude control algorithms on the fly to compensate for sensors that were behaving erratically.
Think about the ingenuity of that. It's like trying to fix a remote control car's physical steering alignment from another continent just by updating its app over Wi-Fi.
Yes.
You can't touch the machine, you can't see the machine, you just have to look at lines of telemetry data and reverse engineer a software solution to force the hardware to behave.
It highlights the absolute necessity of adaptability and redundancy in these salvage missions, because the software has to be robust enough to work around minor, unexpected hardware failures. I mean, a rescue tow truck is useless if it breaks down on the way to the accident.
Exactly. But here's the part of the Swift rescue that I find most compelling, the economics of the intervention. NASA is paying Katalyst $30 million for this mission. The goal is for the Link module to meet up with Swift, physically latch onto it, and use its own thrusters to push the massive telescope back up to its original 373-mile altitude.
Completely fighting against that solar drag we talked about.
Right. So $30 million for what is essentially a physical push, when you look at the balance sheet, is $30 million a bargain to save a 22-year-old telescope that might, just fail next year anyway?
It is an astronomical bargain.
Yeah.
We have to look at the opportunity cost. Let's say NASA hesitates, they don't spend the $30 million, and they let Swift burn up in the atmosphere.
Right.
If the scientific community wants to replace the unique capability that Swift provides, the ability to instantly pivot and catch the highest energy explosions in the universe, you are starting entirely from scratch.
You can't just buy a gamma-ray telescope off the shelf at a hardware store.
You have to secure funding from Congress. You have to design a brand new observatory, procure modern radiation-hardened components, test it for years, and buy a launch vehicle. You are looking at an expenditure of well over $500 million, perhaps closer to $1 billion in today's inflation-adjusted money.
That's massive.
And it would take a decade of planning and construction before it ever saw space. You would have a 10-year blind spot in our observation of the universe.
Well, the explosions keep happening, and we just miss them.
Conversely, for $30 million, which is essentially a rounding error in NASA's broader $25 billion annual budget, you secure potentially 5 to 10 more years of high-quality data from an asset that is already up there, already calibrated and proven to work.
So even if it is old, it's worth it.
Swift is old, yes, but its mirrors and detectors are still incredibly sharp. It is still unlocking the fundamental physics of the universe. Spending $30 million to save a $400 million asset is the ultimate orbital ROI.
It really is.
It showcases the immediate, undeniable value of this new industry. We no longer have to passively mourn our scientific instruments when their orbits decay. We can actively triage and rescue them.
Okay, so we've explored this patient, highly lucrative commercial repair job taking place 22,000 miles away with the MRV, and we've looked at this frantic, high-stakes scientific rescue mission just 300 miles above our heads with the link-saving Swift.
Right.
I think this is the moment where we need to step back and look at the macro picture. Because what we are really talking about here isn't just a couple of isolated, cool science experiments. We are watching the transition from a throwaway culture to a fully managed orbital ecosystem.
That's a great way to put it.
This is the birth of permanent, active space infrastructure.
Framing it as an ecosystem is exactly right. And it's important to recognize that this capability didn't just manifest out of thin air in July 2026. This has been a steady, incredibly difficult technological evolution.
People have been working on this for a while.
If we look at the historical context, Northrop Grumman has actually been the primary pioneer pushing this specific envelope for several years now.
They didn't just start with the MRV, right? They had 2 massive proof-of-concept missions before this, back in 2019 and again in 2020.
Yes, they launched a pair of groundbreaking spacecraft called the Mission Extension Vehicles, MEV-1 and MEV-2. And those missions successfully proved that the core physics and mechanics of the concept worked.
Okay, so they did this before.
They flew out to faltering, out-of-gas communication satellites in geosynchronous orbit, matched their rotations perfectly, and successfully latched onto the dead engine nozzles.
But there is a crucial fundamental difference between what they achieved in 2019 and what they are doing right now with the new MRV, isn't there? The architecture of the mission has changed.
A very significant evolution in efficiency and scalability. In those earlier 2019 and 2020 missions, the entire servicing spacecraft, the tow truck itself, latched onto the dying satellite and simply never let go.
Oh, it just stayed there.
The tow truck essentially acted as a parasitic engine. It fired its own thrusters to keep the old satellite in place, providing the extra years of life, but it meant that highly expensive robotic vehicle was now permanently occupied. It could only ever save one single satellite.
Ah, so that is why the MRV, bringing along 3 separate washing machine jetpacks, is such a massive evolutionary leap forward. The MRV is no longer a parasite, it is a reusable tool.
Exactly.
It flies up, grabs a jetpack, plugs it into the dying satellite, and then physically detaches and leaves. It is not permanently stuck to the first patient it treats.
It exponentially scales the operation. The MRV is a true robotic mechanic, vastly more resourceful and economically viable than the earlier MEV generations. It can service multiple clients across the orbital arc.
Which changes everything.
And the vision Northrop Grumman has for the future of these robotic arms goes far beyond just delivering new gas tanks.
Right, because if you have a robot capable of delicately plugging in a battery, it stands to reason that same robot could perform much more invasive procedures. Are we looking at a future where this minivan just stays up there as a permanent roaming mechanic?
The engineering roadmap absolutely includes highly complex physical repairs of live, functioning satellites in orbit. The 10-foot arms aren't just for pushing jetpacks. Imagine a scenario where a military or commercial satellite deploys in orbit, but one of its massive solar panels gets stuck and doesn't unfurl properly.
Which happens. Mechanisms jam in the cold of space all the time.
All the time. Instead of writing off a $500 million machine because a hinge froze, you send up an advanced robotic vehicle. It flies over, matches the spin, delicately grapples the jammed panel with tactile force feedback, and physically pulls it open.
Just pry it open.
They're also developing the capability to relocate live satellites, entirely moving massive assets from one orbital slot over Europe to a new slot over Asia, without forcing the satellite to burn its own precious onboard maneuvering fuel.
That level of physical manipulation is incredible. But there is a darker, much more urgent necessity to this technology, isn't there? The ability to grapple things in space isn't just about fixing the shiny, functioning, revenue-generating satellites.
No, it's not.
It's about what we are going to do with the dead ones. Because right now, highly trafficked orbits are starting to look like a hazardous junkyard.
The space debris problem is arguably the most critical application of this technology in the long term. Northrop Grumman is actively planning for these robotic vehicles to not just deliver jetpacks, but to latch onto completely dead, unresponsive satellites and physically drag them out of highly trafficked orbits.
Just tow them away.
Tossing them into designated graveyard orbits. And they aren't developing this capability in a vacuum. They are collaborating closely with major defense and research organizations, specifically the U.S. Naval Research Laboratory and the Defense Advanced Research Projects Agency, DARPA.
Now, whenever DARPA gets involved in a project, you know the stakes are incredibly high, and it usually involves national security. Why is the physical removal of dead satellites so critical that the highest levels of the defense sector are stepping in to collaborate on the grappling technology?
It all comes down to a terrifying physical scenario, first proposed by an astrophysicist named Donald Kessler in 1978, known as the Kessler syndrome.
Okay, what is that?
I want you to imagine an orbit like a busy terrestrial highway. But on this orbital highway, the cars are traveling at 17,000 miles per hour, and none of them have brakes.
That's a terrifying thought. Now imagine a massive 3-ton communication satellite dies. Its batteries fail, it loses all power, it can't be steered by ground control, and it can't actively dodge out of the way of incoming traffic. It just becomes a multi-ton dead weight hurtling blindly through the absolute most crowded lanes of orbital traffic.
The kinetic energy involved in collisions at those speeds is almost impossible to comprehend. I know that a microscopic fleck of paint moving at 17,000 miles per hour carries enough kinetic energy to crack a heavily shielded window on the space station. I can't even fathom what a 3-ton dead satellite would do if it hit something.
The physics of hypervelocity impacts are catastrophic. The kinetic energy is so massive that the metal doesn't just crumple, it undergoes a phase transition.
What does that mean?
If that dead satellite collides with another satellite, it doesn't just crash like a car. The materials physically vaporize and shatter. It instantaneously creates thousands of pieces of high-speed shrapnel.
And then that shrapnel keeps moving at 17,000 miles an hour.
Exactly. Those thousands of pieces spread out and act like cosmic duckshot, hitting other satellites in the same orbital plane, which then shatter and create millions of more pieces of shrapnel.
It spirals out of control.
It triggers a runaway, cascading chain reaction of destruction. Eventually, if left unchecked, that entire orbital band becomes a localized hypervelocity minefield. It becomes completely unusable for any future satellites, whether they are commercial internet constellations or highly classified military reconnaissance platforms.
So we're essentially watching the creation of an orbital sanitation department and an armed highway patrol all rolled into one robotic minivan.
Clearing these highly trafficked orbits isn't just an exercise in keeping the cosmos tidy. It is an absolute existential requirement for the future of space exploration and global communications.
Because we rely on them so much.
Modern civilization relies heavily on these orbital pathways for everything. GPS navigation for global shipping, precision agriculture, weather forecasting, synchronized financial transactions, and military command and control. If an orbit becomes a Kessler syndrome graveyard, we lose all those capabilities entirely. These robotic salvage missions are the only way to ensure that the orbital highways remain safe, functional, and clear of hazardous debris. We are moving from a passive observation of space to active, aggressive traffic management.
It is genuinely awe-inspiring to pause and think about what is happening above our heads right this very second.
Yeah.
We started this hour talking about the absurdity of abandoning a luxury car on the highway because it ran out of gas.
Right.
And now we are looking at a reality where a 10-foot robotic arm is wrestling a washing machine-sized jetpack, calculating Newton's third law 22,000 miles away in the freezing void, just to save a corporate asset and shift a balance sheet.
It's incredible.
And at the exact same time, there is a desperate $30 million push to physically lift a sinking gamma ray telescope away from an expanding atmosphere just so humanity can keep watching the biggest explosions in the universe. We have truly, undeniably entered the era of the orbital mechanic.
We have crossed a profound threshold in aerospace engineering. The technology to touch, physically manipulate, and actively alter the trajectory of uncooperative objects in space is now an operational reality. It completely changes the risk calculus of every mission moving forward.
And as we wrap this up, That new reality leaves me with a completely different, slightly more provocative angle to ponder. Because as this technology inevitably advances, as the MRV gets smarter, as those 10-foot arms get stronger, and as autonomous navigation gets sharper, the ability to latch onto, move, or alter the course of any satellite in orbit becomes a tangible reality.
Yeah, this does.
We've spent this time talking about companies saving their own satellites or NASA saving their own telescopes. But if a private corporation or an adversarial government possesses a fleet of highly capable minivan-sized robots that can just fly up, grab, and relocate an object in space, how long until we face intense geopolitical disputes over who actually has the right to move, salvage, or claim the abandoned technology floating above our world?
That is a massive legal gray area.
If a multi-million-dollar satellite has been dead and unresponsive for 10 years, does the first robot to grab it get to claim salvage rights, like a shipwreck in international waters? Does maritime salvage law apply in the deep void? It's something to deeply consider the next time you look up at the night sky and see a satellite tracking across the stars.